Thank you very much for the introduction, Sami, and thanks for the invitation. Yes, today I'm going to talk about some of the works that we have been doing in the context of high-performance tomographic imagery construction. So let's begin. Synchrotron light sources are advanced scientific instruments that are being used by a variety of disciplines. These include material science, biological and life sciences, geo or soil sciences, as well as chemistry, physics, and polymers. So on the left, what you're seeing is one of the synchrotron light sources that is located at the USA. It's actually the advanced photon source, which is at Argonne National Lab. And it's a pretty big synchrotron light source too. It consists of 35 sectors and more than 60 beam lines. And what that means is during the operation time of this synchrotron light source, all of these beam lines can actually perform some experiment and generate some measurement data. And depending on the experiment and imaging technique and the scientific goal, these experiments can actually generate a significant amount of data. Here on the left, what you're seeing is one of the experimental setups in a beam line, which is actually a transmission X-ray microscopy beam line at 32 ID. It is actually specifically located in this sector and in this location. And this beamline basically performs tomography experiments, specifically micro CT experiments. And it can actually generate 10 gigabit per second data while the experiment is collecting data. And depending on the experiment, how long these experiments take, they can actually, the aggregated amount of data that's generated can be in tens of terabytes or even hundreds of terabytes scale. Some experiments takes minutes to finish, some experiments takes hours or days, even for the extreme cases, these can actually take weeks sometimes. And considering this execution time of these experiments and data acquisition rates, as I mentioned, you can actually have tens of terabytes to hundreds of terabytes measurement data. So this basically gives a idea where the advanced photon source is and the computational capabilities we also have at Argonne National Lab. So this is advanced photon source, and here we actually have the one of the supercomputers in the USA, which is the Theta machine. And this is actually pretty useful for us because, as I mentioned, the experiments at the APS, they can generate massive amounts of data. But when the domain scientists actually extract some information out of this data, they actually need to process it. And again, considering the scale of the data, they might actually need to use these supercomputers. And Argonne can actually provide these computational resources to these domain scientists as well as the beamline scientists working at the APS. So Theta machine is a Knights Landing machine. It's a supercomputer, but under the DOE, we actually have other supercomputers too. Summit is another supercomputer that's located at Oak Ridge Leadership Computing Facility, for example. And this computer is a GPU machine. It has more than 4,000 nodes, where each node has actually 6 A100 NVIDIA GPUs. So The data sets that are generated in synchrotron light sources, such as the tomography experiments, such as the tachography experiments also, need to be processed. And considering their scale and computational requirements, they might actually need to utilize these supercomputers. However, you cannot just assume that you're going to submit some jobs with these data sets and get those processed, because you actually need to have efficient computation, efficient algorithms to consume these data sets and utilize these resources in a reasonable way. So in this talk, I'm going to focus on one of the imaging techniques, one of the widely used imaging techniques at synchrotron light sources, which is tomography. And tomographic reconstruction is the typical data analysis tasks that are being performed on these tomography measurements or tomography data sets. And as I mentioned before, since we can generate massive amounts of data, we actually need to do these tomographic reconstruction tasks as efficiently as possible on these supercomputers. So before I move on to the optimizations, what kind of optimizations we need to do on these tomographic reconstruction algorithms, I actually want to give a brief introduction to tomography, how the experimental setups are in tomography and how the data acquisitions are being done. And then I'm going to move on to the tomographic reconstruction. So in a tomography experiment, what we do is we basically put the sample or material that we want to image on a rotation stage. And then we expose this sample to these X-ray beams. And then we collect the resulting X-ray image on a detector. While we're exposing the sample, we actually rotate it. And then this rotation, as a result of these rotations and data acquisition, we collect many of these projections from different angles of this sample. So as a result of this experiment, we end up with these three-dimensional data sets where X and Y axes show the dimensions of these projections, and Z dimension refers to the projections, each of the projections. And this is what you can observe from the on the detector actually. So again, you're basically rotating the sample and it's being exposed to X-ray. And this is, you can actually see how it's being rotated too. So tomographic reconstruction, as I mentioned, is a very typical task that you perform after you're done with your data acquisition. And with the tomographic reconstruction, what we try to do is we basically try to generate 3D volumetric image out of these 3D measurements, 3D projection data sets that we collected during the tomography experiment. So this mapping between 3D measurement data to 3D image, volumetric image of the sample is the reconstruction task, is the tomographic reconstruction. And this can actually be very compute intensive depending on what kind of algorithm you're running and what kind of data set you're operating. The reconstruction problem can be interpreted with this formula. What we try to do is, given an estimated volumetric image and the forward model we have, we try to basically minimize the difference between the measured data. And this is actually a pretty typical inverse problem too. And with some regularizers, you can actually further enhance or increase the convergence of this equation too. So one thing that I should highlight at this point is that one of the geometry that we are using with at the synchrotron light sources At the synchrotron light source, we actually use parallel beam geometry too. And what parallel beam geometry is, we actually have these discrete X-rays that pass through the object. And what this enables us to do is it enables us to treat each of these slices in the 3D measurement data independently be processed. So we can basically extract this slice on the projection data sets, which is called sinogram. And then we can feed this into our reconstruction algorithm and can expect reconstruction algorithm to generate corresponding tomogram, which is a slice in the 3D image. So there are two groups of reconstruction algorithms. One group is called analytical, and the other one is the iterative reconstruction techniques. So there are significant differences between those two categories. Analytical approaches are typically fast, single-pass reconstruction techniques. They basically take only a one pass over the sinogram datasets or the whole measurement datasets and can directly generate the corresponding 3D volume. There are many algorithms that can do this. Filtered back projection and grid rec are two of the widely used algorithms for this. However, this approach, analytical approaches, are typically sensitive to limited data or any artifacts in the measurement data set. The iterative approach, on the other hand, they perform many passes over the measurement data as well as the reconstructed image site. And in each iteration, basically, it tries to converge to a result that is consistent with the measurements. So there are also many algorithms that can do iterative reconstruction. Algebraic reconstruction technique is one of those. SIRT, which is simultaneous iterative reconstruction technique, is another. Maximum likelihood expectation maximization, another one. And model-based iterative reconstructions are actually pretty widely used approach for the iterative reconstructions too. And what iterative reconstruction techniques enable us is they let us integrate system and statistical models in our computations. And as a result of this, we can actually better handle the limited data, those or other kinds of artifacts. On the right side, I actually show some of the results with analytical and iterative approach. For example, this is a shale sample which is reconstructed with grid rec. And there's very limited data in this case. So the resulting analytical reconstruction is extremely noisy. On the right side, you can see the iterative reconstruction. This is much better quality. This provides much better quality. However, it basically requires much more computational resources than the grid rec in order to finish the execution in a timely manner. And we have similar results with bottom two figures too. In left figure, you actually have a lot of artifacts and with the analytical methods are not able to accommodate these artifacts. On the other hand, iterative reconstruction here provides actually pretty clean data. So in this work, we are mainly focusing on iterative reconstruction techniques since they provide much better results, high quality image than the analytical approach. However, again, depending on your measurement data sets, these projection data sets and the 3D volume that you're trying to reconstruct, they can be really computationally demanding. So we actually need optimized algorithms to meet the computational requirements of these reconstruction approaches. In iterative reconstruction techniques, even though you see many of these algorithms, you actually can find the pattern how they perform the data accesses on sinogram space as well as the tomogram space. There are two main kernels these algorithms execute. The first kernel is the projection. This basically performs forward projection on the tomogram space. It simulates the X-rays on the estimated volume, estimated slice. And then once you perform the forward projection, you calculate an error. And then using that error, you perform your back projection and do your updates on the volume. So that the next time you iterate again, perform these projections, your error is more consistent, more ideal with respect to the measured data. So in summary, projection and back projections are the two main kernels that need to be optimized for most of these iterative reconstruction algorithms. And when you look into these rays and how they accesses, how they perform accesses on the matrices, you will see that they actually have irregular accesses on these voxels. So considering the large scale data sets and hundreds of iterations you perform on these volumes, you can actually expect that significant overhead due to these irregular data access and irregular data accesses on the volume. We can, there are two main approaches where you can accommodate, parallelize the projection and back projection kernels. The first one is the compute-centric approach, which we worked a lot on before. And this approach basically performs on-the-fly ray tracing and tries to resolve the race conditions, for example, using replication type of methods. This is efficient in terms of the memory footprint because it again performs on the fly ray tracing. It calculates the index addresses before actually it starts iterations, and then it doesn't remember these pre-accessed locations. So its memory footprint is pretty good. And using the replications, it can also resolve the race condition. However, this basically doesn't solve the irregular data access patterns, the overhead due to the irregular data access patterns that much. And this ray tracing, calculating the index addresses on the fly actually introduces further overhead to the execution. In order to eliminate these overheads, inefficiencies, we actually developed a memory-centric approach. And with memory-centric approach, what we did was we used memorization in order to remember the indices previously accessed. So there's no on-the-fly ray tracing. We calculate indices in advance, store those in some place, and then we utilize those. However, as you can imagine, this memorization operation actually comes at the memory cost, and it really increases the memory footprint significantly. However, this enables us to do many optimizations on the data accesses, as well as, again, it lets you eliminate the on-the-fly ray tracing, on-the-fly index calculations, and so on. The race conditions can also be addressed using the scatter together transformation on the back projection too. We can basically replicate the projection data sets after taking the transpose of it. And then we can treat this as the, we can basically perform the data accesses using the sinogram, as if it is the sinogram data. And since it is, we're changing the accesses from these ray tracing to sinogram accesses, we actually eliminate the interleaving or the intersecting rays with each other. So I hope I was able to give you a good background and what kind of kernels that we are dealing with about the tomography and tomographic reconstruction. Now I'm going to move on to the optimizations that we performed in order to increase the efficiency of these projection and back projection operations. And on the right, what you're seeing is this is the data that we typically acquire during tomography that I showed before. And this is what actually we want to generate at the end. This is the reconstructed image of this volume. And it basically shows us on the Z dimension how the slices are being reconstructed. So let's move on to the data optimizations, the optimizations that we have performed in order to improve the iterative reconstruction computations. So the first optimizations that we implemented was basically data partitioning. So assume that this is our 3D volume. We basically can perform data partitioning in two ways. We can perform the batch parallelization and the data parallelization. So batch parallelism, batch data partitioning in here focuses on the partitioning on the Z dimension. And what it enables us is basically creating these groups of sinograms and assigning those to a single processing unit. And assuming that some of the operations are the same among the sinograms, the slices, and the Z dimension, we can actually combine these operations and perform them at the same time. I will talk about those operations later on, but just to give you a hint, you can actually perform the update operations on the back projections, for example, using fused multiply add operations on multiple sinograms at the same time. So batch parallelism basically enables us to fuse some of the common operations that happen on the sinograms and then apply them at the same time, which improves the computation significantly. Data parallelism, on the other hand, lets you basically partition the data on the X and Z dimensions. And this enables us to decrease the memory footprint or distribute the memory footprint among different processes. So as a result of this, even the memoization method that I mentioned in previous slide introduced a lot of memory overhead. With data parallelism, we can actually distribute this overhead among multiple processes. And this eventually lets us perform really efficient reconstruction on the supercomputers. Here we give what kind of advantage and disadvantage these parallelization, the partitioning techniques have. Data parallelism basically decreases the per process memory because we are basically assigning these sinograms on the X and Z dimension to multiple processes. It doesn't really change anything in terms of the total memory, But since we're basically splitting the same sinogram, for example, among multiple processes, we are increasing the communications. This basically comes because of this property. I mentioned that the slices in the 3D image can independently be processed, but within a slice, we actually need to, if we want to parallelize, we need to perform communication between the processes that share or perform updates on the same slice. Batch processing, on the other hand, doesn't really change anything in terms of the per process memory for a single sinogram, but the total memory increases with the larger batch. So assume that if your batch parallelism is 1, then you're actually assigning all these sinograms on the z dimension into a single process, which needs to have sufficient memory to accommodate. So total memory with the batch parallelism actually increases. However, it doesn't change the communication overhead. So these two partitioning techniques have their advantages and disadvantages. And while you're performing these partitioning, you actually need to consider these properties. So this basically gives an example how the data processors and batch processors communicate with each other. So for example, considering the 0 and 1 processes as well as the 2 and 3 processes, depending on how they are located on the node, their communication behavior can actually change too. So assume that process 0 and process 1 are located on the same socket, they can actually perform really fast communication with each other. However, if they are in different nodes, then you actually need to go through these slower networks. So again, when you're basically mapping your processes to your hardware topology, you might want to consider how they're what kind of links they go through, and this eventually affects the number of batch processes and data processes in your system too. So, as I mentioned, the data access patterns for these X-rays on the tomogram domain and as well as the sinogram domain show irregular properties. As you can see, again, we are showing how a single ray accesses on the vortices on the tomogram domain. In order to optimize this data access pattern, we actually utilized several space filling algorithms. We tried Morton indexing as well as the Hilbert ordering in order to optimize these access patterns. And what we have found is Hilbert ordering actually provides the most efficient accesses. So what does Hilbert ordering do is it basically change the access pattern of the rays so that they are more clustered and cache friendly. So on the right, what you're seeing is what the access patterns actually look like on the projection matrix if we don't do any optimizations or any ordering on the indices. So this still follows relatively irregular properties. But when we apply Hilbert ordering, the accesses actually become much more clustered, and these are much more friendly to the cache utilizations, obviously. We don't only consider the cache utilization when we are performing this Hilbert ordering, though. So when we perform the Hilbert ordering, we actually consider multiple levels. So, for example, our first ordering starts with the thread level decomposition, and then we consider the process level decomposition on later on. These are all consider the Hilbert ordering when they perform accesses on the tomogram space. And then what this also changed is the communication between processes. So starting from the cache up to the inter-process communication, Hilbert ordering actually affects the whole data exchange, how these processes exchange and accesses the data. So you can also consider this not only a two-dimensional problem, but also a three-dimensional problem too. The axes of the rays on different sinograms can actually perform the identical patterns. So what we can do is we can actually batch the sinograms, the z-axes, into groups, and then perform the axes on these groups using the fused operations. And as a result of this, we can basically do much more efficient grouped instructions, apply grouped instructions onto these voxels that correspond to the same x and y coordinates. So here, this probably hopefully gives a better visualization. On a tomography mini batch, we call these the z dimension, batching the data on the z dimension as mini batch, assuming that we are basically operating on this using this tomogram partition, this mini batch in here. When you look into what kind of data accesses you do on the sinogram mini batch, you see this pattern. So what that means is each item, each value you read in here actually tries to access is somewhere in this block. And similarly, on the sinogram partition, when you try to do some operations on this using this value, you actually access it somewhere around this block. So these are still irregular data access. We are not really showing the Hilbert ordered accesses, but it basically shows you what this partition need in the real data set, as well as what this partition need in the tomogram data set. We implemented several optimizations on these volumes. Hilbert ordering and data and batch partitionings are two optimizations we performed, but we also considered computations with different precisions. Specifically, we used mixed precision computations on these data sets in order to provide a higher computational throughput. Specifically, what we did was we basically performed data movement and I/O operations using half precision floating point numbers. But whenever we actually do computation during this projection and back projection operations, we do those computations using single precision floating point numbers. And eventually what this enabled us to do is optimizing the communication data movement, as well as performing the best computational throughput, best computational utilization of these GPUs. The fused multiply add operations can actually be used when we use these mini batches. Again, the z dimensions, when we bundle the z dimensions sinograms together, or the tomograms together, we are effectively be able to utilize these fused multiply and add operations. So this one I already mentioned. We basically utilize the half precision in order to do the data movement, as well as the IO operations. And when you use the mixed precisions, you also need to consider the overflow and underflow issues. So since in some phases we are using this half precision, we can basically, if we don't really utilize the single precision values in the correct places, you can actually hit to this issue of underflow and overflow. So using the single precision, we are basically addressing the overflow issues, and scaling the domains that we are working on. We are addressing the underflow issues that come with the half precision. So mixed precision implementation actually enables us to optimize not only the computation again, but also the communication. So this basically shows our evaluation with different precisions for the projection and back projection kernels. And what we have seen is the single precision and mixed precision configurations provide the best gigaflops. These figures are basically the roofline analysis. It is, if you're not familiar with the roofline analysis, what it shows is on the y-axis, it shows the gigaflops, the computational throughput you get out of the device. And on the x-axis, it shows the arithmetic intensity, which is the flops, floating point operations per byte that's read from the memory. So what we see here is the initial state is basically memory bandwidth for all configurations, but we get again the best performance with the single and mixed precision values among these configurations. And the best values for almost all the configurations, we actually get them with batching almost close to 20 sinograms in our experiments. After 20 sinograms, they actually start, they kind of start degrading their performance. The computational throughput starts degrading. But for the single precision and mixed, they are actually, they are still in a good shape. But the double precision and half precision, they actually start dropping their performance after the 20 batching the 20 sinograms together. And we see a similar behavior for the back projection too. Around 20 mini batch size, we see the best throughput out of these cards. And for this experiment, we are actually focusing on the A100 to this NVIDIA A100 card, which has 40 gigabyte memory. So the other optimizations that we did in order to improve the end-to-end execution time is basically performing the hierarchical communications. But before this basically doesn't show the optimizations on the communication side, but it shows mostly what kind of overheads you can observe during the execution. So kernel here basically shows the computational kernels, and the orange bar shows the communication overhead. And we also have the idle, conjugate gradient, and IO overheads, which are minimum in these cases. The part opt is our baseline. Here we only consider the data and batch partitioning, and also the Hilbert ordering optimizations, what the execution looks like in that case. With kernel optimizations, we also consider the mini batch here and how it improves the execution time. And with communication optimizations, we further basically consider the communications, which I haven't talked yet. But the part that I would like you to actually recognize here is the overall execution times of the double precision, first of all, is higher than the single precision and mixed precision. In other words, mixed precision actually provides the best execution time. And using the mini batch, we can actually minimize the kernel executions significantly. And using different precisions, we can actually optimize the communication overhead significantly too. And we can find the sweet spot, the best execution times with the mixed precision and IO operations in here. There's a significant difference actually. It is around, I don't know, maybe 5 seconds versus close to 80 seconds difference with the most optimized and mixed precision configuration versus the double precision and without any optimizations. And this data set is actually a relatively large data set too. It's an activated charcoal data set, which has the dimensions of 4.5K by 6.4K by 6.4K, I guess. And it is actually a relatively large volume. I think it is around, it should be more than 250 gigabytes of volume that we try to reconstruct. And these results are with 128 nodes too, in which we have 6 GPUs on each node. And even using these, the double precision actually takes a significant amount of time. Though with our optimizations, it is pretty reasonable how the reconstruction, end-to-end reconstruction, what the end-to-end reconstruction looks like. So what kind of optimizations do we do on the hierarchical communication side? So we actually, when we look into a naive communication between the processes, what we see here is the communication is actually pretty sparse in a sense. For example, here, the process 12, assuming that we have this kind of distribution, data partitioning among the processes where process ID 1, for example, has this segment partition of the data, and process 12 has this partition of the data. The way they communicate with other processes basically follows this pattern that we have in here. For example, the process 12, in order to do operations on its own, in order to do the reconstruction, it should actually send data to all the processes that are in this yellow line region. So it needs to communicate with 9, 13, 10, 12, 11, and so on. And if we don't consider any hardware topology or how these processes are mapped to hardware, then this is actually the communication and data volumes you get in your system, how they are being transferred. And this is again very sparse data distribution, data communication among processes. Here you can also see how much data these 3 processes are exchanging with all the other processes. One side note here is when I say a process, I also mean that a GPU actually. So here process 12 is actually mapped to a GPU. And in terms of the GPUs, how they are being organized, We are considering in this context the summit architecture, where again each machine has 6 GPUs, and these GPUs are being grouped into 3 GPUs and connected through 2 power 9 CPUs. So there are 2 sockets. Each socket manages 3 GPUs, and sockets are connected with each other with a slower bandwidth, slower connection. So this naive communication doesn't exploit anything about the hardware network topology that we have in the Summit supercomputer. A better communication is basically performing this hierarchical method. What we can do is we can, for example, consider the groups of GPUs that are connected to the sockets and perform reduce or combine operations within the socket, and then exchange the data later on, whatever combined or reduced between the sockets. And this actually optimizes the data communication significantly. Here, since again, each socket manages 3 GPUs, you will see that only 1 GPU among 3 GPUs are actually being used for the data movement. And this clusters the communication significantly. And as a result, you see that the volume of communication actually decreases between the sockets. You can also do the same thing between the internodes. So there are actually several levels you can apply this communication optimization. The first level you can consider on the local communication within the sockets, and then you can basically consider the communication within the nodes, and then you can consider the communication between the nodes. And this 3-level hierarchical communication significantly optimizes the data volume that is being exchanged on each level. An interesting point here is if you look into the total aggregated amount of data that's being transferred, we actually see that it is larger than the one-to-one communication that we had in here. So with direct communication, the total amount of data we exchange is only 1.35 gigabytes in size for these 3 nodes. However, when we move on to multiple nodes, this multi-level communication hierarchy, we are actually exchanging total of 2.5 gigabytes of data. But the thing is, with this hierarchical communication, what we do here is we are actually performing these local communications inside the socket and between the sockets within the node using a very high bandwidth connections, specifically NVLinks and PCIe connections within the node. So these are very fast operations. And as a result of this reduction, it actually gets much more efficient to communicate through between the nodes. So even though we are increasing the total amount of data that's being moved around, since a portion of these movements are happening using a very high bandwidth connections, we are minimizing the overall communication overhead significantly. We also implemented the communication and computation operations such a way that they are overlapped with each other. So this further improved the overall execution time of our system. And here, it basically shows how the overlapping actually can be done for both projection and back projection operations. So after all these optimizations on these kernels and communication patterns, as well as data access patterns that we did, we actually run these on a real data sets, which is actually significantly large. So this is a mouse brain data set, which has the dimensions of 11K cube. So this is actually a very large data set, and this type of biological data sets are actually important to reconstruct with high quality too, because for example, for this mouse data set, the ultimate goal is to basically detect these blood vessels as well as the neurons, and then performing the segmentation. So the higher quality reconstructions you have with these data sets, the better segmentations you're going to have, and you will be able to deliver a better scientific answer for your problem, or address your scientific goal in a more precise way. So it's important to apply iterative reconstruction on these data sets. However, these can be really large and very difficult to apply. And using supercomputers and our optimizations, we can actually realize these types of reconstructions. So overall, what we see here is the strong scaling performance of this data set, which is again 11K cube dimensions. And as you can see, this is the perfect scalability efficiency line. And considering different stages, different parts of the computation, we see that the sparse matrix operations, for example, shows almost perfect efficiency with increasing number of nodes. Similarly, total execution time actually follows a pretty good efficiency, scalability efficiency, up to almost 2K nodes, and then it's a little bit degrades, the efficiency little bit degrades after 2K nodes. And this is because at this point, the execution time is too short that the IO and communication overheads start showing themselves. And you can actually see that pattern in here too. As you can see, this light blue line shows the IO times. And after 2K nodes, it actually doesn't go as efficient as the perfect efficiency line you see in here. And this basically contributes the overall execution time and messes up with the efficiency after some point. However, at this point, this is using the 4K nodes, GPU nodes, we were able to actually do the whole mouse brain reconstruction in 2.5 minutes, which is actually pretty impressive by itself. And this is, when I say 4K nodes, this is actually the whole Summit supercomputer too. And we utilize the whole Summit computer actually has this 24K GPUs. So I talked about the optimizations that we did in order to improve the iterative reconstructions. I talked about the data partitioning, domain decomposition using Hilbert ordering, hierarchical communications, and I showed you what kind of results we got. In our group, we also do machine learning accelerated reconstructions on the streaming tomography data sets too. I don't know how I'm doing in terms of the timing right now. I can probably go over these really fast and then start taking your questions. Here, what we did was in this work, we considered the problem of reconstructing the streaming tomography data sets in real time. As I mentioned to you before, these tomography experiments can actually take a lot of time to finalize. A tomography experiment can actually take days to finish. And it is actually good to have reconstructions in real time while the experiment is happening, so that we can provide some feedbacks to the data acquisition processes and so on. So in this project, what we focused on is performing the reconstruction on the streaming tomography datasets. And while we are reconstructing these, applying the machine learning techniques to improve their quality. And in order to do that, we used a runtime system called TraceX. TraceX basically performs these iterative reconstructions, parallelizes the iterative reconstructions, and performs those efficiently using large-scale computer resources. There are several parameters you can adjust in order to change your computational requirement, as well as your image quality, delivered image quality. These include the window length, which is actually the sliding window buffer, which accommodates the streaming tomography projections, number of iterations that you apply on this sliding window, and number of frequencies you trigger the kernels that I mentioned before, the projection and back projection kernels. So these three parameters basically define your computational requirements during the stream reconstruction operations, as well as what kind of image quality you want to have at the end. The TraceX uses reduction-based processing model. This is actually the compute-centric reconstruction technique. However, it actually shows very good scalability, and it performs well with medium-scale data sets. And we have actually shown its results using Mira supercomputer as well as the Theta supercomputer too, using this 32K cores and 64K cores respectively. So this basically shows what kind of machine learning architecture we used. This is the generative adversarial networks. And what it does is it enhances, denoises the given image according to its trained model. It utilizes this UNet in order to do the denoising. UNet is typically being used for segmentation, but here we are using it for the denoising and image enhancement goals. And it also uses the neighboring sinograms, neighboring reconstructed slices to basically provide better, higher quality images. So what does this pipeline look like when it runs? So here we are basically showing that this is the measurement data. This is the normalized measurement data. And focusing on this sinogram, this row of this projection, what the reconstructed image looks like. So during the experiment, you actually will see this image if you don't do any image enhancement. However, if you apply machine learning, Tomogen, our denoiser image enhancer to this output, you actually get a pretty clear reconstructed image. So we evaluated this method too. The dotted lines basically show the Tomogen enhanced image with respect to different number of projections. In other words, you can also treat this as the timeline. And their respective quality metrics. This is structural similarity index. And what we see here is with even after processing 400 projections, almost all the configurations that apply denoising or image enhancement method that we developed provides better image quality than the ones that we don't perform any machine learning, apply any machine learning. And this is like this shows the different reconstructions again with respect to the projections, acquired projections. The bottom is the conventional method without applying any machine learning, but the upper line, the green line, shows the proposed method. And again, even with the early points, 400, 200, after receiving 200, 400 projections, we see much better images compared to the proposed method. So what are the takeaway messages? Efficient and scalable algorithms enable science. What we have seen is the synchrotron light sources, the experiments get much more complex. Their data generation rates also increase significantly. And we actually need these efficient and scalable algorithms to accommodate the requirements of these highly advanced instruments and experiments that are being performed on them. In fact, the X-ray brilliance actually increases almost 3 times in every 18 months. What that means is in some imaging techniques, you can expect this much increase in their data acquisition rates. However, when we consider the computer speeds, Moore's law, we know that we can only expect 2x increase in the computer speed in every 18 months. So we basically, the X-ray brilliance and data acquisition rates increases significantly more than the computer speeds, which makes it much more demanding or important to develop these efficient and scalable algorithms for these highly advanced scientific instruments. We implemented several optimizations for sparse computations. We performed shared memory tiling, register tiling, and mixed precision operations, which eventually provided us almost 34% of the theoretical GPU throughput that is being provided by the Summit supercomputer. And this actually goes to petabyte scale. I think we arrived around, we were able to provide 64 petaflops during the iterative reconstructions with our optimizations. We also performed optimizations on using hierarchical communications and batch processing pipeline, which provides 2.5x speed up compared to without these optimizations. And we have shown that we can actually reconstruct a very large experimental data sets, which were not done before, actually. And yes, so we were able to exceed 65 petaflops computational throughput on Summit supercomputer. And I also talked about the reconstruction on streaming tomography datasets and showed how the machine learning can actually improve the overall reconstruction quality and provide us reasonably well reconstructed images, even in the very early stages of the experiments. So with this, I want to thank you for your attention. I also need to acknowledge Mert Hidayetoğlu. Matt is the person who actually did most of the work. He did lead the optimizations on the iterative reconstruction part, and he did all the experiments. So these are some of the papers that we have published, and the latest paper that we published on SC20 also received the Best Paper Award. And you can find more information about these techniques in this paper too. So at this point, this is all my presentation. Apparently I exceeded my time a little bit, but I can probably take a couple more questions, or I don't know how however you want to accommodate. I have time to take questions.
Okay, thank you so much.
It is Sunday at the end today, so.
Yeah, so the whole day for us, okay? Thank you so much, Tekin. This is a great talk, of course. So I want to ask our colleagues here if they have any questions to start with.
I have one. I have actually a comment on the question. I'd like to, emphasize again the great takeaway message of your last slide, where investment into software give you perhaps a greater return of investment than in hardware, right? I mean, in this kind
Yes.
of application. Then I have the question about, so you use mixed precision.
Yes.
So what is the impact of using mixed precision on this tomographic reconstruction? Did it, were you still able to get the accuracy of, the required accuracy as if you were doing everything in double precision, for instance?
Yes. So that's actually a good question. So with the mixed precision, that was one of our concerns actually. With mixed precision, what we do is we do the data movement with half precision, but the computations we do with the single precision. And this normalization and denormalization phase, where we cast the half precision to single precision and single precision to half precision, we don't actually lose that much of precision during that translation. And we actually looked into that too. I think I didn't put those in the here, but do you still see my screen?
Yeah.
Okay. So, okay, here it is. So this is how the convergence change with respect to different, probably I should make it more closer. Different precisions. And as you can see, with a higher number of iterations, we actually distributed the iterations with respect to time, because with different precisions, you might actually have different number of iterations at any given time too. But what we have seen is for the double precision, we didn't even have a very, so residue, the single precision and the mixed precision, when we compare, the difference is not that much significant actually. And we even see that the mixed precision at some point gives better results, in most of the case, better results than the single precision too. We don't really know why we're getting the better results with the mixed precision, but I mean, the convergence actually seems better with the mixed precision.
Okay.
So I hope this answers your question. But the main take is computations are still being done with the single precision floating point numbers, and we perform the communication and I/O operations with half precision. And during this normalization, denormalization operations, we are actually doing some tricks too. For example, we are changing the domain that we are operating on. We increase the voxel sizes, artificially increase the voxel sizes, so that the half precision operations do not introduce any issues, like they don't do underflow and so on. So there's some synthetic optimizations that we do in order to handle the half precision operations during our reconstructions.
Okay, thank you.
Mm-hmm.
Okay, do we have another questions here from the audience?
Thanks, Bicer, for your nice presentation. Very impressive on the presentation of the hybrid how do you call that? Hybrid ordering, 3D hybrid domain decomposition, and use that in order to reduce the communication pattern on GPUs, on sockets. And I have a few questions related to this the 3D hybrid ordering. And what is the block size that you are used? And the 3D hybrid ordering that you shown, it looks more like a 2D hybrid ordering with the third dimension, which maintains the third dimension. Do you think it can the method can be generalized into a real 3D? I mean, the real 3D hybrid ordering. And do you see any other scientific domain that can benefit your finding? Thanks.
So let me address the later questions that you have first. So I can definitely see the application of this data access pattern using the Hilbert ordering on different areas. And in fact, people have used these space filling algorithms in order to optimize the cache utilization before too. This is new in this context, iterative reconstruction context, and its application to these communications between the processes within this GPU, within this Summit supercomputer hardware topology. It is new in this context, but previously people actually used the space filling algorithms in order to optimize the cache utilization. In our context, tomographic reconstruction, we applied it. I can also see the application of this space filling algorithms to other imaging modalities, imaging techniques too. So whenever you have these irregular data access patterns on your data accesses, if you see some clustering opportunities, they actually can be applied, and you can expect some performance increase with these. So your question, yes, I definitely see application of this on different domains, and in fact, in my case, in different imaging modalities. The other one that you mentioned on 3D space, if there's any opportunity to do this on 3D space, these space filling algorithms, it is also possible. In our case, I mentioned that each sinogram can be processed independently, if you recall. So in that sense, it is fine to stay on the 2D space. You can actually just perform your Hilbert ordering on the 2D space and expect reasonably well performance increase. However, if your rays actually intersect, cut through the several sinograms at the same time, then you might actually need to do the 3D Hilbert ordering. There you can expect performance increase. In our case, if you're just working on the 2D space and your irregular access patterns only are happening on the 2D space, 2D Hilbert ordering is sufficient to get maximum performance. But again, if your data access patterns are irregular in the 3D space, in that case, you can expect 3D Hilbert ordering, 3D space filling algorithms to provide performance increase. And we actually have those types of experiments at APS too. For example, laminography is one of the experiments that single ray can intersect multiple sinograms. And in that case, it makes sense to use Hilbert ordering on 3D space. And your first question was what the block size is. I can't really recall the block size. I'm sorry for that, but it should be written in the paper.
Okay, I think we passed the time by 15 minutes. It worth it, but I think that's okay for today. Thank you so much, Tekin, one more time. And hopefully you will have more future talks and collaborations. And hopefully you enjoy walking up early today?
No, it was a pleasure actually. So thank you all for inviting me, and we are pretty open to collaborations too. We please feel free to get in touch with us, and similarly, I would love to connect with you guys too. Again, thanks a lot for inviting me.
Thank you so much.
Thank you.
Thank you, Tekin. Thanks a lot.
Thank you.
Thank you too.
Okay. Bye.